The topic of today's webinar is building mechanisms in MapleSim. Now let's just go over the agenda. So the first part of this webinar will be on seeing how to build some simple planar mechanisms in MapleSim, going over a few techniques to see how you can build models efficiently. And the next part of the webinar will be looking at some of the standard analysis tools that we have to perform analysis on those models, and also looking at options for customizing those analysis. Now let's just open an empty MapleSim model. This is how MapleSim looks like. The center area is called the canvas, where you can drag and drop components to build your model. On the left side is where you have the built-in library components in place, categorized under different domains. MapleSim has about 900 and so library components defined here. So some of the domains are signal blocks, as you can just expand through them to find the components. And once you see them, you can just drag and drop it here. Now, a few other domains that we have are electrical, 1D mechanical, multibody, hydraulics, and so on. But today's focus will mostly be on the multibody session of the library components here. Now, going over a few other settings quickly, the right side is where you have the property pane, which is empty at the moment because there's no components defined in the center. And then we have the simulation setting that helps you define the solver type, the solver, and of course a few other settings for step sizes and so. And then we also have a multibody setting where the gravity is defined and the direction of the gravity is also defined, and a few other settings for visualization. Now let's just go ahead and build the first model for today, which is a simple pendulum model. I'm going to go into multibody, select bodies and frame, and drag in a fixed frame. Now this fixed frame marks as the reference for my system, and I'm going to drag in a rigid mass. A rigid mass acts as the center of mass for my system, and I'm going to drag in two rigid body frames and place it right over here, so the center of mass will be exactly in the center between the two links. And you can notice that as I click on each of these components, the property tab on the right highlights. Now, for example, for a rigid mass, you can see that we can change the mass of the system, the rotational inertia can be defined, and also the initial conditions can also be defined. I'm going to leave everything to default for now and just go ahead and bring in the last component to finish this model, which is a rubber joint. A rubber joint provides a 1 degree of freedom rotation about the axis that I specify. I'm going to leave it to default Z for now and simply connect all of these components together. So I have a simple pendulum model. Now let's just change the length of the pendulum to be a total of 1 meter. So it's going to be minus 0.5 because it's facing towards the reference axis from frame A to frame B. And I'm going to make this plus 0.5 because it's facing away. And I'm going to hit simulate. So once the simulation is complete, the simulation window will automatically open up. There you go. I'm going to hit simulate, and now you can see a simple pendulum model oscillating in space for 10 seconds, purely acting under the force of gravity. Now let's just say that I want to build a double pendulum model. I can simply do that by copying all of these components together and placing it right beside the model, and just connect them like this. Let's say that I want to change the length of the second link to be twice the length of the first link. I can do that by changing the length here, make it -1 and +1, and simulate the results. So once the simulation is complete, the simulation window will automatically open up. So here's my 2-link pendulum oscillating in space. So these are just a few quick examples to show how we can build models in MapleSim. Now let's just go ahead and build the first mechanism for today, which is a slider crank mechanism. I can simply do that by editing the components that I have here. All I'm doing is adding a rubber joint to my link 2, and also adding a prismatic joint and constraining it to move in the x-axis, which is the default here, which I'm going to leave it as such, and connect the components together. So now I have a slider crank mechanism. Let's just place it like this. So now I have a simple slider crank mechanism, which is unactuated at the moment because I've not given any actuation to them. Now, let's say that I want to add or measure certain values at certain points in my model. I can simply do that by selecting this attach probe option here and selecting on the port that I want to measure. So in this case, I'm measuring the displacement of my prismatic joint with time. So once the simulation is complete, the simulation window will automatically pop up. Perfect. I'm just going to rearrange. And it's already in the front view. This is a plot that I want to measure. And when I hit simulate, I can see a slider crank mechanism acting under the force of gravity, and I can also see the displacement plot in the bottom. Now going back to the model, you can notice that as I click on each of these joints over here, apart from the ports that I've used to connect the components together, you can see a few extra ports on the top, which says flange B and flange A as I hover over them. Now these flanges act as a port or a gateway to connect 1D mechanical components to the multi-body system. Now let's go into multi-mechanical and see what we have there. So we have options called rotational and translational. Let's go into rotational. We have another options that asks. So we have rotational and translational option. Let's go into rotational. So we have torque and motion drivers. I'm going to select the motion driver and I can locate a component called constant speed. So let's drag that in and simply connect them like this. And let's say that I want to actuate the crank at 2 radians per second and simulate the model. So now my slider crank mechanism is actuated to move at a constant speed of 2 radians per second. There you go. So now when I hit play, you can see the system at a constant speed, and I can also see the displacement plot here. Perfect. Now let's just go ahead and look at the second model for today. So this is a model or a mechanism that converts reciprocating motion to rectilinear motion and vice versa. So this is the simulation recorded video of the MapleSim model that I've put in here, and this is also the schematics or the layout of the system. So quickly going over the layout, so I have a slider of length L pinned at the top here, and I'm applying a force at an x-axis to the tip of the slider. I also have a horizontal slot here that is moving in the x-axis, which is located at an offset of h from the reference point. Now all I'm doing is coupling both these motions together so that they move relative to one another. So going back to the MapleSim model, so this is how the completed model looks like. Now you can notice that the layout remains the same, but I've added a few extra components to boost the visualization for the system. So quickly going over the first part, so this is the slider that I've defined. Now this is a step force I'm giving at an x-axis near the tip of the slider here. And here is where I've defined the horizontal slot, which is moving in the x-axis. And all I'm doing is providing a 2 degree of freedom motion to the slot here, by allowing it to move or rotate about Z using the revolue joint and move in the local Y of the slider axis. Now you can notice that apart from the components that I've used to build the system, there's an extra block here which is called the parameters block. Now this parameter block allows you to define the parameters of your system at the top level of the model. Now this becomes quite useful when you're dealing with complex systems where you have many subsystems inside. You don't have to go inside each subsystem to change the parameter. Instead, you can define them in the top level here. Let's just simulate the model now. So once the simulation is complete, you can open up the MapleSim model simulation window. So now when I hit play, you can see the simulation for 10 seconds. Now what I'm going to do is I'm going to save this results as original. Perfect. So now I'm going to go into the parameter block and change the mass of the slider to 5 kgs and re-simulate the model again. So now I have both the results overlapped on top of each other. Let's just change the color of the original result to gray so that we can differentiate the system. And I'm going to hit play. And now you can see how the dynamic response is for both the systems. And of course, it's quite expected because the system with heavier mass oscillates more compared to the one, let's just play the simulation. And now we can see that both the results are overlapping on top of each other, and the system with lighter mass oscillates more compared to the heavier mass, which is quite expected because we're applying the same amount of force to both the systems. Now these checks becomes quite useful when you're dealing with systems that have many varying parameters and you want to see how the parameters will affect the dynamics. You can simply do that by changing it and overlapping the results with the original model and seeing how the system response is. I'm going back to the presentation for the next model, which is a quick return mechanism. So I have the simulation recorded video here of the MapleSim model and the schematics of the quick return mechanism. The main application of this mechanism is built in a way that the time taken for the forward stroke of the crank is slower compared to the return stroke. Now this becomes quite useful in the industry where they use shaping machines. Now here is where I've defined the schematics. So I have a slider of length L pinned at the top, and I also have defined a crank which is located at a certain offset from the reference, and the length of the crank is defined as LC. And now I'm coupling the motion between both the systems here, and you can see that the quick return ratio is the ratio between the forward and the return stroke. Going back to the MapleSim model. So this is the quick return mechanism. The first part remains the same as we've seen for the previous model. So this is the slider that I've defined, and this is the crank over here, which is located at a certain offset. And now I've given a constant speed component to actuate my crank at 2 radians per second. Now all I'm doing is coupling both these systems together by applying a 2 degree of freedom motion to the tip of the crank, allowing it to rotate about Z and move along the x-axis of the slider here. I've already simulated the model, so let's open up the simulation. I've also probed the results for omega and the torque. And when I simulate the model, we can see a quick return mechanism moving at a constant speed of omega. Let's just go back to the model and say that I want to apply a spring and a damping force to the revolute joint of this slider. So I can simply do that by putting in the numbers for spring and damping constant. And let's first save the original model, saying it to be original, and go back to the system and resimulate. So what I'm doing here is I'm applying a 2 radians per second constant speed to my crank, and I've also, I've applied a 2 radians per second constant speed to the crank, and I've also defined a spring and a damping constant to restrict the motion here as well. So when we see the simulation, right now both the simulations are overlapping on top of each other, the plots are also overlapped. In order for the system to remain at a constant speed of 2 radians per second, you can see the increase in the torque to compensate the spring and the damping force. Perfect. Now let's just go back to the next mechanism, which is a rack and a pinion mechanism. So this is a system or a method that doubles the stroke length of the rack here. So just giving a brief description about the parts. So I have a connecting rod that communicates with the pinion that is rotating in between a top and the bottom rack. Now this connecting rod is actuated by a crank here that is moving at a constant speed. Now you can notice that for one stroke length, the connecting rod communicates with the pinion, which in turn communicates with the top movable rack to move it to twice the stroke length because the bottom rack is fixed. If the bottom rack was movable, you can see the pinion communicating with both the top and the bottom rack for equal stroke lengths. Now going back to the system. So this is the schematics of that model. So the first part is very similar. It's a slider crank mechanism that we've seen previously. The crank is actuated at a constant speed of 1 radians per second. Now all I'm doing is I'm introducing a component called ideal gear rotational to translational, which converts the linear motion of this link 2 here to rotational motion of the pinion. Now I'm again defining the same component here to convert this rotational motion to the linear motion of the top rack by means of defining the transmission ratio. So this is exactly how this model is built, and you can again see the simulation results on the window. Of course, when the bottom rack is mobile, we can see the system transmitting equal stroke lengths for both the strokes or for both the racks. Now going back to the simulation to look at the next part of the webinar, which is understanding how we can perform analysis on the system. Now I've taken the same quick return mechanism here. Now MapleSim, though it has more than 900 built-in components in place, it allows the user to create custom components specific to the user needs. Now in this case, I'm going to create a custom component and connect the component to the MapleSim model to simulate the results. All I'm doing is calculating the quick return ratio for this mechanism. We've already discussed that the quick return ratio is the ratio between the forward and the return stroke, and I'm doing it by taking the omega curve for one cycle, because one cycle is all is needed to calculate the quick return ratio. The equations that I'm using is defining the return stroke and the forward stroke of my omega curve and simply integrating the time taken for the return and the forward stroke, and later dividing the ratios or dividing the values to get the ratio of the quick return mechanism. So going back to the model, let me open up. So it's already open here. So you can see that this is the same quick return mechanism that we've seen earlier, and this is a new custom component, Medelica component, that I've used to define the equations, and I've connected it to the revolute joint of the slider. Now let's quickly open up. So you can see that the first part of the code is defining the input, which is flange A, which allows me to get the measurements from the revolute joint. The output is of course the ratio. I'm defining the parameters here. I'm saying that when my omega is greater than 0, which is my return stroke, separate the curve, and omega is less than 0, separate the curve, and I'm simply integrating the time taken for the return and the forward stroke and calculating a ratio here. Let's go back to the model. So I have attached a probe to measure the quick return ratio. So once I've already simulated the model, so you can see the simulation results. So this is the omega plot, and this is the quick return ratio here. Of course, it calculates the ratio from 0 to the end of cycle time, but we are more interested in the last value, which is exactly at the end of one cycle, which is 1.7. Now let's say that I want to change the ratio, or I want to see how the ratio changes by changing a certain parameter value. I can simply do that by selecting the apps and templates folder over here. So these are all the list of apps that MapleSim has that the user can use to perform analysis on the model. Now in this case, I'm going to select the parameter sweep app. So what this parameter sweep app does is it allows me to change a certain parameter value within a range and see how that affects the dynamics and response of the system. And let's go to the parameter sweep app. So this load system option will allow the MapleSim to connect its model to this parameter sweep application here. So below is where I've defined the parameters that I want to change. In this case, I'm changing the length of the crank from 0.2 to 0.3 meters for 5 data points. And now the output that I want is the quick return ratio, and I'm selecting the last point of the quick return ratio, which is what is needed. And going down, I'm going to hit run parameter sweep. So this will basically display the plot of the quick return ratio with respect to my crank length. Going down and selecting the parameter, which is the crank length. So now you can see that as the crank length increases from 0.2 to 0.3, I can see the rise in the quick return ratio, which is expected. So this app allows the user to perform some quick checks to see how changing parameters affects the response of the system. I'm just going to quickly close it and go back to the presentation for the next part of the analysis, which is for the model that I've showcased earlier, which converts reciprocating motion to rectilinear motion. So all I'm doing here is calculating the natural frequency of the system. Of course, when you're doing it by hand, it becomes quite a tedious process where you have to define the equations of motions, get the eigenvalues, and calculate the natural frequency. And if in case you want to change a parameter value, you'll have to recalculate the whole results again. Now here, I'm going to show you how we can do the exact same thing, but by using Maple Worksheets. Going back to the model. So this is the same model that I've showcased earlier. All I have to do is select the apps and templates folder and select the worksheet option here. So by selecting on this worksheet option, MapleSim will be connected to Maple Worksheets, where you can use Maple coding language to perform analysis. Now I already have a completed worksheet here. I'm going to simply open it. So this is the MapleSim model, and this is a Maple worksheet. Now by using the link model command here and simulating it, my MapleSim model will be linked to this Maple worksheet, and I've assigned a variable A so I can call the variable to get all the items that I need from the MapleSim model. In this case, by simulating or by using the command get parameters, I can get all the top level parameters that I've defined in the MapleSim model. So these are all the parameters that I've defined. And here, the next part is I'm calling the linearization command. Now what this linearization command does is returns the linear form of the MapleSim model. So from there, I can compute the state. I can easily get the values from the state space matrices, which allows me to calculate the natural frequency. So this is the omega that I've obtained, and I'm keeping everything symbolic because that becomes quite useful, where if you want to change a parameter value, you can simply insert them in the final equation over here and get the results. So now I'm defining the parameter again and then calculating the natural frequency. So we know the natural frequency of the system is 0.53 Hertz. Now going down, all I'm doing is redefining the same parameter, but I'm making the mass of the slider and the offset of the horizontal slot to be symbolic. So this allows me to change or give a certain set of ranges to this mass and see how that will result, or how the natural frequency will be. So next, I'm computing the natural frequency. So you can see that my M and H are symbolic. And now I'm giving a range or a set of values to change the mass from 1 to 5 kgs and plotting how the natural frequency will be by keeping the offset as a constant. So here you can see that as the mass increases, the natural frequency reduces for the system, which is an expected result. Now going further down, here what I'm doing is changing the offset of the horizontal slot to move along the slider axis and see how the results are. I'm going to simply simulate it and plot the results. And now you can see that as the slot moves from the reference to the slider axis or along the slider axis, I can see a reduction in the natural frequency. This is also as expected because when the horizontal slot is almost near the reference point, you can see that the moment of inertia of the slider has no effect on this horizontal slot. And now as it moves further down the slider axis, you can see the effect of the horizontal slot on the moment of inertia of the slider, and that is why you have the reduction in the natural frequency. So these are just some few quick examples to see how we can build mechanisms and perform analysis on the system. So that ends the presentation for today.